Hey, good morning. My name is Akshay, and this is Rodrigo, Cameron, and Clarissa. We are HAND, which stands for Hand and Neural Network Design. And for the past year, we've been working with Dr. Tedeschi at the Humanoid Biorobotics and Smart Systems Lab on a breakthrough in the field of speech-controlled robotics. Specifically, we were able to develop a first-of-its-kind end-to-end convolutional neural network, or CNN, for speech control of a robotic hand. The novel breakthrough here is the end-to-end structure, which means that our network takes in a raw speech spectrogram as its input and directly outputs the logical voltages for each of our muscle channels. Our prototype allows you to speak into the microphone, and then a robotic hand will show the number you say.
So our neural network has two convolutional layers, which, based on our research, is the most adequate to get the speech features out of the speech. It also has two fully connected layers, where the second connected layer has, it outputs 5 for our 5 fingers. We also have, for our training, we used excuse me. So for our training, we used an open source speech data set, and we also use, not regression, what was the word?
Mean squared error.
Mean squared error for our loss function. So for this project, the overall, pardon me, continue.
All right, so that CNN neural network is hosted on a GPU that takes the speech input from a microphone and converts it into digital values, ranging from 0 to 1 for each finger of the robotic hand, with 0 being fully relaxed muscles and 1 being fully contracted. So this digital values from that GPU is sent to a custom-designed PCB printed circuit board that using I2C, which is a digital communications protocol. On the PCB, we have an 8-channel 16-bit digital to analog converter that takes the digital values from the GPU and converts them into analog ones needed by the robotic hand. On the PCB, we have a dedicated channel for each of the muscles, and each channel has regulated power supply, the digital output from the converter, and an operational amplifier circuit that takes these analog signals and converts them to the high voltage levels needed for those muscles to actuate. Our board currently supports up to four channels for the muscles, and it can easily be expanded using external ports.
Yeah, and so as far as applications go, with a little bit of fine-tuning, we could see several potential things, such as prosthetics or robotic assistance. But one that we're most excited about is speech-to-sign language translation. Because our neural network is end-to-end, we can train on any language and any number of words pretty easily. So we could go from any language to American Sign Language, and we can operate any robotic hand from 0 to 16 volts. So we're pretty excited about the marketability and the scientific contributions we've made with this project.
So when you train this, how do you annotate your, how do you convert from the speech? How do you, because to do that neural network training, you're going to have annotation somehow by telling which finger to hold the hand. So how did you force that learning? How did you train that?
So the data set we have is the Google Speech Command data set, and it has sets of text and pieces of audios, right? So it's designed for, say, speech-to-text machine learning or something like that. So what we have is a map that we use during training only that says this word, this string word, say ONE1, corresponds to these positions for the robotic hand.
So you're not using true natural language understanding, you're using phrase matching, more or less. So it's like, number 1, push your finger up.
But the network does not see the string of the text at all, right?
Oh.
During training, the network only knows that the input is this piece of audio and the correct answer are these 5 voltages.
Oh, okay.
Right?
Okay.
So that's what makes it end-to-end.
All right, I got it.
Any other questions?
Can you repeat what you just said about sign language and also the different dialects or?
Right, so because the our current, what we do is we have you say a number, like 4, and then the hand will hold up 4 fingers. What we can do is we can train it on like the American Sign Language alphabet, so we could say a letter and then it could hold up the position for that letter. We could do words with a sequence of letters.
Or we could potentially do multiple hands in the future and have it do, a word in translation to both hand positions.
Right, so any like word that we have the speech data for, we can train the network on and just set it to a hand position.
Yeah, the way the network is structured, you can add as many words as you want in any language you want, and it's very easily expandable for a very large vocabulary.
How about the different dialects or?
You would just need speech samples in that language or that dialect.
Currently, what's the capacity? I mean, what's your command set?
So currently we're doing numbers. So 0,
Number.
1, 2, 3, 4, 5.
5
Right.
6 digits.
Right,
Yeah,
but as we
so-
said, we can easily, as long as we have data, we can add more to that.
Why do you think you can scale it up?
Sorry?
So normally with a classification network, the output is the size of the number of words you recognize. So that means if you want to recognize more words, you have to change the network, right? With this structure, the output is always of size 5. So just given more data, you can use a pre-trained network and just train it more.
So your output class is only 6 of them.
No, output class is, there's no classification happening here.
It's a continuum
The output
range.
is just a continuous output or regression output for the 5 muscle voltages.
But your resolution is going to go down as your vocabulary goes.
The resolution meaning,
I mean, if you're, say, if you had a number 4 and a number 3, you know the 3 distinct classes. But 3.75 to 3.7501, you are not aware
oh no,
of the output.
the numbers are just as
The
like
larger the vocabulary.
integers. Yeah.
We're almost done.